Hello and welcome. This video is a follow-up to my last video. If you haven't seen it yet, you should watch it first, because otherwise you'll miss a whole bunch of context. There's a link in the description. In that video, I've posed a few questions to flat earthers. Predictably, not a single flat earther has stepped up and even tried to answer any of these questions, and all the responses I've received were of the "nuh-uh" variety. However, one response stood out a little bit in that it was a slightly more specific "nuh-uh", and it basically went something like, "You haven't proven that the signal actually came from the sky." Which I found odd, considering that somehow the signal knew exactly when to appear and when to disappear, and even knew when not to appear because it was behind a hill from my very specific location. But okay, we can ignore that and use this opportunity to look at a different way through which we can know where the signal came from, and that is the antenna. In order to do this, we'll have to look at a bit of antenna theory first, so we can understand what we're looking at afterwards. And then in the second part of the video, we can see this in action. The simplest kind of antenna is this kind. These are monopole antennas. They're basically just a single wire or a rod or something, any kind of conductive material. A step up in quality is a dipole antenna. This is basically two monopoles end to end with the wire connected in the middle. These antennas are what's called omnidirectional, and that's a bit of a misnomer because they don't actually receive or transmit in all directions. They do receive equally well all around here, so basically any direction that's perpendicular to the antenna. But the steeper the angle gets, the worse the quality gets, and in the direction the antenna points to, it doesn't actually receive very well at all. This can be measured, and it can also be simulated and calculated, and then you can plot it in a 3D graph, which then looks something like this. The shape is a little bit like a donut. Now moving on to the antenna that I've used. If you're old enough, you will probably remember seeing quite a lot of those. These are old terrestrial TV antennas, and they use the same design. Yagi antennas are also used for applications like wildlife tracking, and that is exactly for the same reason why I'm making this video. These antennas are directional. You have to point them at the source of the signal in order to get a good reception. And this is how you can use them to track wildlife. You simply point them in different directions, and wherever the strongest signal is, this is the direction of the transmitter. Here is a small one I've made for a different project. The only active element is this one. This is actually a dipole, and you can see the antenna connection here in the middle. This one is called the driven element. By itself, this dipole works like any other dipole, but the presence of all of these other elements here, that's what makes the difference. These are all passive, they're not connected to anything, but they still work as an antenna, and because of this, they act as a kind of a repeater of the signal that it receives. That means that each of these elements produces a copy of the signal with the phase shifted slightly. And all of these elements are spaced out in such a way that right here where the driven element is, all these repeated signals, they overlap and produce constructive interference. So basically right where the driven element sits, you get an amplification of the signal. All of this only works if the elements are spaced out correctly and the signal is coming from the front. The further away you turn the antenna from the signal, the less effect you get, and in the worst case you can actually get destructive interference at the driven element and the signal more or less disappears. And just with a dipole, this can also be measured and calculated and simulated and then plotted on a 3D graph, which looks something like this. So very clearly there is a very strong directional component here. And this is how we know that whatever direction we point the antenna to, that we get the strongest signal. This must be where the signal is coming from. So now let's see this in action. I got my tracking app. The satellite path is already in progress. And right now the satellite is pretty much straight overhead. The setup is pretty much the same as in the last video, except that I'm tracking NOAA 19 instead of NOAA 18. And instead of SATDUMP, I'm using SDR++. Because it has a little bit of a nicer waterfall display, and it enables us to make an additional bonus observation. More about that at the end of the video. Now let's start by establishing a baseline, point the antenna to where the tracker says it should be coming from, And we can have a quick listen. Yep, sounds familiar. Nice and strong signal. And now let's see, does it maybe come from the horizon over there? Nope, that's clearly worse. Back up, double check. Yep, there it is. Over there maybe? Nope, also clearly worse. Double check again against the sky. Yep. Is it coming from there? No, there's mostly noise there. It's coming from the sky. So far this is not looking good for flat Earth. Maybe over there at the horizon. Nope, also clearly worse. Maybe over there. No, also not from there. This is coming from the sky. Look at that. Well, let's try a few more directions. Maybe over there towards the house. No, that's just noise here. That's probably the fridge running. Definitely nothing there along the horizon. Anywhere from here. Nope, definitely not there. Just more noise. Over at the horizon gets a little bit better, but back up in the sky, that's where you get the nice strong signal. Maybe if I hold the antenna the other way, maybe this is a polarized signal. Let's try that. From the sky, still nice and strong. From the horizon, not so much. Clearly worse. Let's try over here on this side. Anything there? Nope, 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 nope. Just noise. This is the laptop, just noise. Weak signal, nothing to see there. Back up in the sky. Yep, there it is. It's almost as if this signal actually comes from the sky. Who would have thought? By now the satellite is already pretty low, but let's have another look along the horizon. See if we're able to pick up a stronger signal from anywhere there, but it's still the same result. Noise from the kitchen, noise from the laptop, weaker signal from anywhere else along the horizon, and if we point it back up to the sky, there it is. Now we can do a quick double check against straight up where the satellite was at the beginning of the pass, but now it's clearly worse, which means the satellite has obviously moved quite a bit. And there you have it, successful tracking of a satellite along the sky. So now let's look at the second thing that we were able to observe just now. If you were watching very carefully, you might have spotted it, but probably not. Here I have a screenshot from the signal from the beginning of the pass at the top, and another screenshot from the end of the pass at the bottom. If you're looking very carefully, you can see that the signals don't quite line up. The one at the top is a little bit to the right, and the one at the bottom is a little bit more to the left. It's a little bit hard to see, but it becomes a lot more obvious if you look at the whole recording and run it in a time lapse, and you can just watch the signal slowly shifting to the left as the pass is ongoing. What you're looking at is Doppler shift, and we can actually use this to figure out how fast the signal must have been going. Doing so requires a bit of math, and we all know how flat earthers are with math, so I'll just go through it very quickly. We just look at the screenshot and figure out how big of a difference in frequency there was. It seems to be about 4.3 kilohertz. We take the Doppler shift formula for change in frequency. We can rearrange it to solve for a change in velocity. We plug in the numbers, and we get about 33,000 kilometers per hour. Now, since this is the difference between the satellite approaching us and the satellite going away from us, the ground speed normally would be half of that. But at the same time, we didn't capture a full pass, and the satellite also wasn't coming at us directly, so the actual ground speed would be more. But anyway, we can ignore that, because I think 16,000 kilometers per hour is a good enough number for me to again ask the question, what kind of balloon is this? What kind of plane is this that can go this fast? I guess we'll never know. See you next time.